понял, поворачивается вектор. Все, да, я понял, это одно и то же, супер.
Ну да, ну ладно.
Ладно, потом расскажешь по противоречию.
Будем начинать?
Да.
Okay, so at the previous lecture we...
Вы трансляцию включили?
А?
Трансляцию включили?
At the previous lecture we discussed inductive limits of locally convex spaces. And in particular we have seen that in general locally convex inductive limits are rather mysterious objects as compared to projective limits. For example, let's recall that if we have a projective limit of a family of locally convex spaces, xi, and if we assume that each space xi is equipped with a defining family of semi-norms, then it is very easy to to construct explicitly a defining family of semi-norms on X. But if X is the inductive limit of a family of locally convex spaces, then in general there is no explicit way of constructing a defining family of semi-norms on X, even in the case where Xi are normal spaces. Of course, there are some exceptions of this rule, and you'll find such exceptions in our exercise sheets. In particular, in the last exercise sheet, there are some exercises where, for example, when we consider the space of continuous compactly supported functions on a sufficiently nice topological space, then it is possible to describe explicitly the standard inductive topology of the space by a quite explicit family of semi-norms. This is also possible in the case of finitely supported or compactly supported smooth functions on an open subset of Rn, but in this case the respective family of semi-norms is slightly more complicated. There are some other important examples of inductive limits where the family of semi-norms can be defined explicitly, but in the general case there is no explicit way to construct such a family. Another phenomenon is that if we deal with projective limits, and if all the spaces xi are Hausdorff, then the projective limit is also Hausdorff. And we will see today if they are complete, then X is also complete. But for inductive limits, the situation is unpredictable. For example, I will have just discussed an example in which all xi are balanced spaces. And there are countably many balanced spaces, but the inductive limit is very non-Hausdorff. It contains a codimension 1 subspace with the anti-discrete topology. And today, our first goal will be to discuss an important special case of inductive limits, which are quite well behaved. And then we will discuss strict inductive limits. Strict inductive limits. So suppose we have an inductive system of locally convex spaces xi, and with connecting maps phi ij, indexed by a directed pose set A. An inductive system of locally convex spaces. We say that this system is strict. If all the connecting maps phi ij, which act from xi to xj, are topologically injective. For all I and j such that I is less than or equal to g. And the inductive limit of a strict inductive system is called strict inductive limit. Strict inductive limit is the inductive limit of a strict inductive system. Okay, so this is our definition. Formally, it applies to arbitrary arbitrary directed process I, but as a rule, this is a remark. As a rule, strict inductive systems are considered only in the case where I is just a set of natural numbers, equipped with the usual order relation. So this happens because it is exactly this case where strict inductive systems are especially well behaved. Okay, so let's consider some examples. Example 1. Vector space, say X, of countable dimension, equipped with the strongest locally convex topology. With the strongest locally convex topology. So let's observe that this is a strict inductive limit of finite dimensional spaces. It's isomorphic to the inductive limit of finite dimensional spaces Kn. Actually, this was observed already at the previous lecture, but now let's observe that this inductive limit is strict. This is a strict inductive limit. Well, indeed, Kn is naturally embedded in Kn plus 1, and of course this embedding is topologically injective. So this is strict inductive limit. Example 2. Suppose that X is a locally compact second countable topological space. Second countable Hausdorff topological space. For example, the real line, or an open subset of Rn. And let's choose a compact exhaustion, Kj, a compact exhaustion of X. That is a sequence of compact subsets such that the union is X and such that Kj is contained in the interior of Kj plus 1. We know that in this case, the space of continuous compactly supported functions on X is isomorphic to the inductive limit of the Banach spaces C, K, N of X. And again, this is an inductive system, an inductive sequence. So there are countably many such set spaces. So Ckn of X consists of those continuous functions on X whose support is contained in Kn. And it's a Banach space with respect to the usual supremum norm. And this is a strict inductive limit. It's a strict inductive limit. Actually, the natural embeddings of the spaces into each other are isometries with respect to the usual supremum norm. So they are isometries, and moreover, they are topologically injective.
Is the notion of strict limits useful in other fields, in other categories, or just in this one?
Maybe, but I have never seen this notion outside the field of topological vector spaces.
Okay.
Maybe, but actually, it can be naturally in the context of general topology, or in the context of Topological vector spaces. Formally, it can be defined in any category because actually a topologically injective map, the property of being topologically injective can be defined in category theoretic terms, well, it's a good exercise. And then, by using this categorization, we may formally generalize this definition to an arbitrary category.
As just a monomorphism?
No, not just a monomorphism. There's a notion of strict monomorphism. And now I'll not give you a precise definition, but there is a notion of strict monomorphism, which makes sense in any category. And by using this notion, we may generalize this definition to the context of an arbitrary category. But I have never met applications of such a general definition. Okay, example 3. Example 3. Yeah, monomorphism. A monomorphism in the category of topological vector spaces is just an injective continuous linear map. And here we have topological injective. Okay, example 3. We might take now we might take any open subset of Rn. Again, take a compact exhaustion. Of U. And consider the space of smooth compactly supported functions on U. This will be isomorphic to the inductive limit of the respective spaces C infinity Kj of U, which consists of those smooth functions whose support is contained in Kj. So each space in this sequence is equipped with the same topology induced from C infinity of U. And so the respective injections are topologically injective. And so this is a strict inductive limit. Strict inductive limit. Now, another example. And an exercise at the same time shows that not all natural inductive limits are strict. Let's take a point, 0 in the complex plane, and let's choose a base, let's say script U, a base of open bounded neighborhoods. On this point. We may assume that it is countable. And that each UN plus 1 is contained in UN. For example, we can take just open the, we may let UN to be the open disk of radius 1 over n, centered at this point. And let's consider the space of germs of holomorphic functions at this point. So I have already used this notation. Let's let me write this once again. So this is the space of germs of holomorphic functions at this point. So we know that this space has a natural locally convex topology, and we know that this is the inductive limit. We can take, for example, the spaces of holomorphic functions on the respective neighborhoods, or we can take the spaces of the Banach spaces of those holomorphic functions which are continuous on the closures of the sets Uj. So a script A consists of continuous functions on the closure of Uj, which are holomorphic on Uj. So we have such an isomorphism, we have this isomorphism and this isomorphism, but none of them is a strict inductive limit. They are not strict inductive limits. In other words, the respective connecting maps in these sequences are not topologically injective, in spite of the fact that they are normally injective. If the sets are connected, then if the sets Uj are connected, then these maps are injective, but they are not topologically injective. So the inductive limits are not strict. Okay, now let's. Our next goal is to prove the following theorem, which shows that strict inductive limits of sequences of locally convex spaces are rather well behaved. So suppose that we have a strict inductive sequence x1, x2, x3, and so on is a strict inductive system sequence of locally convex spaces. Then, well, I don't introduce any special notation for the connecting maps because they are topologically injective, so we can obviously identify each space in the sequence with a topological vector subspace of the next space in the same sequence. x1 is a subspace of x2, x2 is a subspace of x3, and so on. Then, first of all, I claim that so, well, let x denote the inductive limit. Let x denote the inductive limit of this sequence. Then first I claim that x is Hausdorff if and only if all these spaces are Hausdorff. All the spaces xn are Hausdorff. Property 2 for each n, for each natural n, the natural map from xn to x. So, since x is the limit, the inductive limit of the sequence where each n will have a natural map from here to here, I claim that it is topologically injective. And moreover, xn is closed. X. Again, we identify xn with respective subspace of x by means of this map, so I claim that it is closed in x. Okay, so now suppose, moreover, suppose also that each xn is closed in xn plus 1. Oh, sorry, I had to assume this earlier. Not here. Okay, let's assume it from the very beginning. I'm sorry, maybe some parts of the theorem don't need this assumption, but let's, for convenience, assume this from the very beginning. I apologize for this correction. So let's also suppose.
The complete.
No, I don't know what complete is. We'll discuss completeness a bit later today, but completeness is not assumed now. Suppose also that xn is closed in xn plus 1.
Мне кажется, хотел сказать, что вот странно будет, если взять и просто пополнить что-то один раз, а потом зафиксировать.
So we suppose that it is closed, then I claim that xn is closed in X for every n. For every n. Property 3, you have a sequence xi, x. I claim that it converges in X, even only if it is contained in some of the steps, in some of the spaces xn, and converges in xn. xi is contained in xn for some n, and converges in this space. And property 4, I wouldn't say that this is a good property, but this is, well, this is life. I claim that if this sequence doesn't stabilize, then X is not metrizable. X is not metrizable. Unless the sequence xn stabilizes. Which means that for some n, xn equals xn plus 1 equals xn plus 2, and so on. Well, so this is our theorem. To prove this result, we need a few lemmas. Number one, suppose that X is Topological convex space, and Y is the vector subspace of X. First, I claim that for every absolutely convex neighborhood of 0 in Y, say V in Y, there exists an absolutely convex neighborhood of 0 in X. Say U, such that V is U intersected with Y. And second, I claim that for every continuous seminorm Q on Y, every continuous seminorm can be extended to a continuous seminorm on X. There exists a continuous seminorm P on X such that Q is the restriction of P to Y. Okay, so let's prove part 1. First of all, let's observe that here the key statement is, key property is the absolute convexity. Because, of course, by the definition of the induced topology, if V is an open set in Y, we can always find an open set in X such that this property holds. So the point here is that U can be chosen in such a way that U is absolutely convex. Okay, so to prove one, let me first draw a picture. So suppose that this is Y. This is Y. This is V. So as a first step, we find an absolutely convex neighborhood of 0. Neighborhood of 0 W in X such that the intersection of W and Y is contained in V. And here's the picture. This is W. This is possible because the space is locally convex, and just by the definition of the induced topology, such W always exists. And now we define U explicitly. Let U be the convex hull of the union of V and W. And I claim, and this is a little exercise, that U is what we need. It is convex by construction. It is circled because, well, V and W are both circled. The convex hull of a circled set is circled. So U is absolutely convex. And it's a simple exercise to show that the intersection of U, this is U, the intersection of U with Y is exactly V. Part 2 is immediate from part 1. Well, indeed, we take Q and we apply 1 to the unit ball of open unit ball with respect to Q. This gives us the neighborhood of 0 U, and now P will be the Minkowski functional of U. Okay, so this is lemma 1. Lemma 2 is in fact an analog of a well-known fact from the classical functional analysis. Suppose that X is a locally convex space and Y is a closed vector subspace. Then, for every element in X which doesn't belong to Y, there exists a continuous linear functional f on X such that f vanishes at Y but doesn't vanish at X. Well, probably you are familiar with this fact in the context of Lorentz spaces. And for locally convex spaces, the proof is exactly the same. We observe that, first of all, we consider the quotient of X modulo Y, and we denote by Q the quotient map. We now observe that the quotient is a Hausdorff locally convex space, because Y is closed in X. This is the Hausdorff locally convex space, and Q of X is a non-zero element of the space, because X doesn't belong to Y. And we know that continuous linear functionals on the Hausdorff locally convex space separate the points. So there exists a continuous linear functional G on the quotient such that G doesn't vanish on Q of X. And now to define F, we simply take the composition of G and Q. This is a continuous linear functional on X, and it doesn't vanish on X by construction. Okay, lemma 3, this is the last lemma we need for proving the theorem. Lemma 3 is a simple but useful trick of proving non-metrizability for concrete spaces. Suppose that X is a metrizable topological vector space, and Xn is a sequence in X. I claim that there exists a sequence of positive numbers of positive real numbers, such that lambda n xn converges to 0. The proof is very easy. Since X is metrizable, we can find a countable base of neighborhoods of 0. So let's choose a countable base at 0. We may choose it in such a way that each un plus 1 is contained in un for all. Just by taking a suitable intersection. So first we choose an arbitrary countable base, and then we replace u2 by the intersection of u1 and u2, u3 by the intersection of u1, u2, and u3, and so on. And in this way we get a decreasing chain, which is a base of neighborhoods of 0. Now, since each neighborhood of 0 is an observing set, for each n we can find a positive number lambda n, such that lambda n xn belongs to un. This is because un is observable. And now it's clear that since this is a base of neighborhoods of 0, it's clear that lambda n xn goes to 0. Because since this is true, lambda n xn sits in un, then lambda n plus 1 x n plus 1 also sits in un, and so on. And so they converge to 0. This is useful if we want to prove that x is not metrizable. Because if we want to prove that x is not metrizable, it's enough to construct a sequence xn for which there is no lambda n with this property. Okay, so now we're ready to prove our theorem. Well, let's look once again at the statement. So let's start with part 2. So we will see that these injections, these maps from xn to x are topologically injective. Okay, so let n be a natural number, and let un be an element of 0 in xn. We apply now lemma 3. Oh, sorry, not lemma 3. This was lemma 1, if I'm not mistaken. Okay, so this is, we apply this picture. This was lemma 1. So by lemma 1, there is well, an absolutely convex. Absolutely convex neighborhood of 0. By lemma 1, there is an absolutely convex neighborhood of 0 un plus 1 in xn plus 1, such that un is the intersection of un plus 1 and xn. And then apply the same argument to un plus 1. And so on. So we get a chain un plus 1, and so on. Each nu I is a neighborhood of 0, an absolutely convex neighborhood of 0 in xi. And ui plus 1 intersected with xi equals ui. For all I, for all natural I. Okay, let's now just take the union. Let U be the union of these sets taken in X. not from 1, but from n. So clearly U is an absolutely convex absorbing set. An absolutely convex absorbing set. And the intersection of U with every xi is a neighborhood of 0. So this implies that U is actually a neighborhood of 0 in X. So let's recall that in general, when we construct the inductive locally convex topology generated by the family of maps, then the standard base of neighborhoods of 0 in X consists of those absolutely convex absorbing sets whose preimages under the canonical maps are neighborhoods of 0. In this case, the preimages are just the intersections. All of them are neighborhoods of 0, and so U is a neighborhood of 0 in X. So on the one hand, it is a neighborhood of 0, but on the other hand, the intersection of U with the initial space Xn is by construction just Un. So this the neighborhood from which we started. So this implies that the map from Xn to X is topologically injective. Actually, I've said nothing about injectivity of this map, but this is a part of one of the propositions which were discussed in the previous lecture when we discussed injective inductive limits. The respective result, which was actually an exercise for you, included the injectivity of the respective maps. So this map is actually not just injective, but it's topologically injective. And it's a simple exercise now to show that the image is closed. Xn is closed in X. Actually, it is in this place where we need the closedness of Xn in Xn plus 1. So far, we didn't use this assumption. But to show that Xn is closed in X, we have to assume that Xn is closed in X plus 1 for every n.
Есть топологическое утверждение, да, что у нас есть просто как бы гомеоморфизмы на образ, мы берем объединение, чтобы это не значило топологических пространств. Здесь имеет какое-то значение все эти?
Более не менее, тонкость в том, что когда мы определяем индуктивную локальную выпуклую топологию, значит, база окрестный раз следует из абсолютно выпуклых, вот здесь важно, поглощающих множеств вот с этим вот свойством. Но в принципе очень легко вот этот кусок очень легко переписать в контексте просто общей топологии.
Сейчас, вот при этом топология не получается автоматически просто топология объединения. Ну, в смысле, получается. Вот
на самом деле получается, для строгих индуктивных пределов получается. В общем случае нет, но для строгих получается. Строгих получается. Okay, so this was part 2. Let's now look once again at the statement. So what else? So we must also prove that X is Hausdorff if and only if all the spaces Xn are Hausdorff. This is part 1. Well, it's clear that if X is Hausdorff, then Xn is also Hausdorff. Because, we have a continuous injection of Xn into X. And this implies that if X is Hausdorff, then Xn is also Hausdorff. And the interesting point is to prove the converse. So suppose that all the spaces, so we prove the right to left application. So suppose that all the spaces Xn are Hausdorff. And we want to show that X is Hausdorff. Actually, to prove that X is Hausdorff, we will show that continuous linear functionals on X separate the points. This clearly implies that X is Hausdorff. So we take a non-zero point in X. since X is the union of the step spaces Xn, we can find n such that X belongs to Xn. And since Xn is a Hausdorff locally convex space, we find a continuous linear functional f 0 on Xn such that f0 doesn't vanish at X. We already know that Xn is a topological subspace of X, that is, the inclusion is topologically injective, so we may apply the Hahn-Banach theorem together with the already proved part 2, which states that Xn is a topological subspace of X. And this implies that f0 can be extended. There exists continuous linear functional f on X such that f extends f0. Now, by construction, f of X is not 0. And since X was an arbitrary non-zero element, we conclude that continuous linear functionals on X separate the points, and so X is Hausdorff. Okay. Part 3 is about convergent sequences. So let's look at the statement. We want to show that if xi is a sequence in X, then it converges in X if and only if it is contained in Xn for some and converges in Xn. And again, the right to left implication is clear. If it is contained in Xn and converges in Xn, then of course it converges in X, because the map from Xn to X is continuous. So we want to prove the left-right implication. Well, assume that it's not the case. Assume that there is no such m. We will also assume that Xn belongs to big Xn, but well, we just assume that little Xn doesn't belong to big Xn for every n. We might just take a suitable subsequence of the initial sequence, and the respective subsequence will satisfy this condition. And we will also assume that Xn converges to 0. In general, it converges to some vector x, but we may consider Xn minus x, a new sequence Xn minus x, which converges to 0. Okay. So we want to get a contradiction. And to get a contradiction, we will explicitly construct continuous seminorm on X, such that Xn doesn't converge to 0 for this seminorm. Well, how can we do it? We apply lemma 2. If I'm not mistaken, this was lemma 2, about, which states that closed vector subspaces can be separated from points by linear functions. So we apply lemma 2, and for each n, we construct a continuous linear functional f of x such that f vanishes at xn, but such that f of little xn is not 0. Actually, we may also suppose that this is a positive number an. If it is not positive, then we simply multiply fn. We simply multiply fn by a suitable number. So this shows that we may choose fn in such a way that this is positive. Okay, and let's now consider the following seminorm of x given by the following formula. P of x sum f j of x over aj, or 1 to infinity. First of all, let's observe that this is a well-defined function on x, because if we fix a point little x, then it belongs to some xn, but because of this property, only finitely many sums survive, and we actually have a finite sum from 1 to n. So this is well-defined. And moreover, P is actually a continuous seminorm. P is a continuous seminorm on x. Why is it so? This is a continuous seminorm on x simply because its restriction to each xn is a continuous seminorm. If we restrict it to xn, we have finitely many summons. Each of the summons is obviously a continuous seminorm. So we have the sum of finitely many continuous seminorms. And this is true for every n. So for every n, P, the restriction of P to xn is a continuous seminorm. And by the definition of the inductive locally convex topology, P is a continuous seminorm on x. If we now calculate P of xn, this is clearly greater than or equal to the nth summoned, fn of xn over an, and this is 1. As a result, we see that xn doesn't converge to 0, and this is a contradiction. So this contradiction completes the proof of part 3. We have proved that if xn is a convergent sequence, then it is contained in some of the spaces xn.
А эти два последних утверждения топологически просто не верны, да, в общем случае?
Какие
пространства. Ну, что объединение, во-первых, вот такое вложенных, замкнутых друг в друге пространств Хаусдорфовых Хаусдорфова, это, наверное, неправда, да. Непонятно, с чего бы это было правда, а может и правда.
Просто в контексте общей топологии, с обычной индуктивной топологией, мне кажется, что правда. Ну, сейчас я сходу вам не скажу, но, по-моему, надо подумать. Но интуиция подсказывает, что правда. Ну, в общем, на досуге и вы подумайте, я подумаю.
А происходимость?
Но происходимость уже не знаю. Я вам точно не скажу. Да, тут все специфическая такая локальная картинка. Сейчас сходимся точно вам не скажу. А вот насчет, может быть, тоже правда, кстати. А насчет философности, по-моему, должно быть правда. Okay, now finally part 4. We have to show that if the sequence doesn't stabilize, then the inductive limit is not metrizable. And here, lemma 3 will be useful. Let's look once again at lemma 3. Oh, where is it? It was here. No? Well, I'm lost. Oh! For some strange reason, it is on page 6. Okay, so this is lemma 3. So to prove that x is not metrizable, we explicitly construct a sequence xn and x in such a way that there is no such sequence lambda m. And this will be very easy because we already have part 3. So for every m, let's choose an arbitrary element xn, which belongs to xn but doesn't belong to xn plus 1. Xn minus 1. Then, for every sequence lambda n of positive numbers, lambda n xn has the same property. And so part 3 shows that lambda xn doesn't converge to 0. And now lemma 3 implies that x is not metrizable. Okay, so this completes the proof. Here's a concrete example of the situation. Again, we take the space of smooth compactly supported functions on an open subset of Rn. And by using this theorem, we already know that this is a strict inductive limit of metrizable locally convex spaces. So this theorem implies that the space is Hausdorff and is not metrizable. Hausdorff and non-metrizable. And this theorem also explicitly describes the convergence in the space. A sequence Fj in this space converges to some function f, even only if their supports are contained in the same compact set. There exists a compact set K in U, such that the support of each of them is contained in U, and the support of F is also contained in U, and such that, K, well, sorry, this was K, contained in K, and the supports are contained in the same compact set, and their partial derivatives converge uniformly on K for every multi-index alpha. So this is the standard convergence of smooth compactly supported functions. By the way, in many elementary textbooks devoted to distribution theory and written for non-mathematicians, this space, the space of smooth compactly supported functions, is not equipped with any topology, but instead it is equipped with the convergence. And this is exactly this kind of convergence. But we are mathematicians, and for us topology is also important. So now we see that this standard convergence of smooth compactly supported functions is actually determined by the standard inductive topology on the space. Okay. Another important class of inductive limits, which are reasonably well behaved, consists of so-called compact inductive limits. Let me suggest a few words about this kind of inductive limits. So if I have an inductive system of locally convex spaces, then the sequence is called compact if all the connected maps are compact. Well, so far we have defined compact linear maps between topological vector spaces. So the definition is similar to the case of normed spaces, namely a linear map between topological vector spaces is called compact. If there is a neighborhood of 0 in Xi, such that the closure of its image is compact. It turns out that for compact inductive limits, there is a complete analog of our theorem. In particular, a compact inductive limit of countable inductive system of Hausdorff spaces is Hausdorff. It is not metrizable unless the sequence stabilizes. The convergence in the limit in X is described exactly as in our theory. So a sequence converges if it is contained in one of the step spaces and converges in this space. And a typical example of a compact inductive limit is this non-example. So these two inductive limits are not strict, but it can be shown that they are compact. So in some sense, these two classes of inductive limits are disjoint, except for trivial cases. Strict inductive limit is not compact, and a compact inductive limit is not strict, because topologically injective linear map is almost never compact in the infinite dimensional case. But both kinds of inductive limits share the same good properties. Well, I will not prove anything about compact inductive limits for time reasons, and because the proofs are not very easy. So now our next goal will be to discuss. Where's the last page? Okay, so this is the last page. So our next goal will be to discuss some useful topologies on spaces of linear operators. Of course, you know that if x and y are norm spaces, then the space of bounded linear maps from x to y is also a norm space in a natural way. But what if x and y are topological vector spaces? In this case, there is a rather general way of topologizing the space, but actually there are many choices for such a topology. So suppose that x and y are locally convex spaces, and suppose that B, script B, is a family of bounded subsets of X. We will take the family of all bounded subsets, or we can take the family of all finite subsets, or we can take the family of all compact subsets. Actually, there are many other natural choices. Now, for each set in this family, we can define a seminorm. Seminorm, which will be denoted by PB on the space of continuous linear maps L of xy by the following formula. PB of T will be the supremum of P of T of X, where X runs over B. This is finite because B is a bounded set. The image of a bounded set, it's a simple exercise to show that the image of a bounded set under a continuous linear map is bounded.
B is the norm on Y?
Excuse me?
What is P?
Oh, sorry. For every P and for every continuous seminorm P on Y. Thank you. I forgot to say what P is. So P is a continuous seminorm on Y. So it's a simple exercise to show that T of B is bounded. The image of a bounded set under a continuous linear map is bounded. And so the supremum is finite. So as a result, you get a family of seminorms on L of xy on the space of continuous linear operators. By definition, the topology, the respective locally convex topology on L of xy, generated by all such seminorms, P, B, where B runs over our family script B, and P runs over the family of all continuous seminorms on Y. This topology is called the topology of uniform convergence, on elements of B. Well, and let's denote it. Say T B. And the space L of xy equivalent with this topology will be denoted simply by LB of xy. Okay, so why is it so cold? Well, here's an exercise which explains the terminology. I claim that a sequence so Tn in L of xy in LB of xy converges to an operator T if and only if it converges uniformly on every element of our family script B. What does it mean? This means that for every neighborhood of 0, U and Y, and for every B, there is a number such that for every x in B, Tn of x minus T of x belongs to U. And for every little n bigger than n. So this explains what the uniform convergence is. It converges uniformly on every set from our family. The second exercise, which is also quite easy, is that when we define the respective topology for space of linear operators, we may restrict to a suitable family of a suitable defining family of seminorms on Y. So if big P is a defining family of seminorms, on Y, then the same topology is generated by the family of seminorms of the form PB, where B runs over our family script B, and P runs over the defining family big P. So it is not necessary to consider all continuous seminorms. We may consider only some defining family. It's also rather easy to describe explicitly a subbase of neighborhoods of 0 in this topology. To describe this subbase, let's introduce also some notation. If, say, B is a subset of X and U is a subset of Y, let M of B U denote the set of those linear operators from X to Y, such that T of B is contained in U. Then, it's rather easy to show, this is an exercise for you, that if U is, script U is a subbase of neighborhoods of 0 in Y, that's the base at 0 in Y, then sets on the form M of B U, where B runs over script B, and U runs over script U. This is a subbase of neighborhoods of 0 in the space of linear operators. Okay, here are some important special cases of this topology. Special cases. For example, we can take the family of all bounded sets, bounded subsets of X. In this case, the respective space of linear operators is usually denoted like this. We just write little b here. This means that we consider the uniform convergence on the family of all bounded subsets. And in a special case where Y is the base field, the standard notation is X prime beta. This is the so-called strong duo. The strong duo of X. By the way, let's observe that in the case where X and Y are norm spaces, if X and Y are norm spaces, then the space LB of XY is just the space of bounded linear operators equipped with the topology generated by the operator norm. Operator norm topology. It's rather easy because, well, informally this means that uniform convergence on all bounded sets is equivalent to the uniform convergence on the unit ball. And uniform convergence on the unit ball is determined by the usual operator norm. The second special case is the case where, it's, in a sense, this is opposite to case 1. This is the case where B consists of all finite subsets. Of X. In this case, the space of operators from X to Y is sometimes denoted by LS, little s of XY. And if Y is the base field, what we get is the so-called weak dual space of X, and this is denoted by X prime sigma, the weak dual. Clearly, the respective convergence for this topology is nothing but the pointwise convergence. So the topology on the space is nothing but the topology induced from the space y to the power x, where y to the power x is equipped with the product topology. Also, we can take, for B, we can take, for example, the family of all compact subsets of X. And in fact, there are many other possibilities, some of which will be discussed in the second half of our course when we discuss duality. Okay. Well, probably that's all for today. Our next goal will be to discuss complete locally convex spaces, complete topological vector spaces, and in particular, complete locally convex spaces. Discuss some of their basic properties, and some examples of complete spaces, and discuss completions of locally convex spaces. In particular, we will see that the completion of an arbitrary locally convex space can be described explicitly as the projective limit of a suitable family of Banach spaces. And in particular, this will imply that every complete locally convex space is a projective limit of Banach spaces. Okay, thank you.